Hello viewers, welcome to my channel ITJ Olympiads and AP Physics with Ambarish. And today I've brought a very interesting video that's about the shapes of the hanging chains. Like you might hang a flower garland or any chain. So we want to know what kind of shape does that chain take. And it's a problem from David Morin, which is about and such a shape is called actually catenary, and we'll try to find out the equation of catenary in this video. So let me state the problem. So here's the problem. A chain with uniform mass density per unit length rho hangs between two given points on two walls. So this is a chain and it's hanging here and it's hanging from two pegs like this. Okay. Find the general shape of the chain. We have to find the shape of this chain. So even though it's not given in problem, if you want, you can use this as the origin. Take bottommost point as the origin, and then think of vertical as y-axis and horizontal as x-axis, and try to find the equation of the chain as y as a function of x, and of course there will be some arbitrary constants of integration which will depend on the location where it is tied. So all those things we'll try to evaluate later on. Okay, so it says aside from arbitrary additive constant, the function describing the shape should contain one unknown constant, and the shape of the hanging chain is known as catenary. So I hope first part of the question is clear. We have to find the shape of this chain, and I have asked you to take this as the origin, even though not mentioned in problem, but it will simplify things a bit, I feel. Okay, then the unknown constant in your answer depends on the horizontal distance d between the walls, so and the vertical distance lambda between the support points. So this vertical distance between the support points is lambda between these 2 points. Vertical distance is lambda and horizontal distance is d. Okay, okay, and the length L of the chain. So it will also depend on what is the total length of the chain. Okay, so it will depend on d, lambda and L. Okay, find an equation involving these given quantities that determines the unknown constant. So we do not have to find out the unknown constant, but we have to develop an equation in unknown constant. Okay, so this is our problem, and that equation we can solve using a computer. We need not solve that equation by hand, but we just need to find an equation involving these quantities that determines the unknown constant. So it turns out in first part you will be getting an unknown constant, which we have to find a method for evaluating in part B. So if you want, you can give it a try. It's a fairly complicated problem. I mean, it depends how you take it. If you want, you can give it a try, or if you want, you can have a look at my solution right away. So I'll get into the discussion. Okay, so let's say this is our chain, and for horizontal equilibrium of the chain, it is important that horizontal tension should be same everywhere, right? Because if you take any section, then whatever is the tension component in the horizontal direction here, same should be the tension component horizontally in this direction, because in the horizontal direction there's no gravity. So what I have written, for horizontal equilibrium of the chain, the horizontal component of tension must be constant, and let this value be F. Okay, so let's say horizontal tension is F. So if the horizontal component of tension is F, then what is the vertical component of tension? Let's say this chain makes an angle theta with horizontal somewhere. So if this is F, then vertical must be F tan theta, right? Simple vectors. So if this is F, then this is F tan theta. So on this element, let us say this angle is theta, so downward force because of tension becomes F tan theta, and here upward force becomes F tan theta plus d theta, because here the angle is taken as theta plus d theta. Okay, so considering the FBD of a small element of the length dl, we can say that, see, vertical force is F tan theta plus d theta, downward force is F tan theta. So net upward force due to the tension is F tan of theta plus d theta minus F tan theta, and this should be balancing the mg of the chain element, right? So that's what I've written, F tan of theta plus d theta minus F tan theta is equal to, now what about the length of this segment? See, if suppose this horizontal length is dx, then the slant length becomes dx sec theta, right? So, and rho is the density per unit length, so then this becomes rho dx sec theta into g. That's what I've written, rho dx sec theta into g. So that's the force balance for the element. Okay, and now look at this very carefully. See, tan of theta plus d theta is what? That is the value of slope dy by dx at x plus dx, right? Dy by dx at x plus dx, and this is dy by dx at x. and so if you subtract the two, so it becomes change in slope. So change in slope divided by dx is the change in the x coordinate. So change in slope upon change in x coordinate is nothing but rate of change of slope with respect to x, which is nothing but the second derivative, right? So if you take f common here and if you subtract these two, this simply becomes and you take this dx downstairs here, okay? So tan of theta plus d theta minus tan of theta divided by dx, that becomes y double dash, right? Okay, and then okay, and sec theta, if you want, you can write sec theta is what, see, sec theta is nothing but tan theta is dy by dx, and sec theta is 1 plus under root of 1 plus tan square theta, and tan square theta is what, slope y dash. So instead of writing the sec theta, I have written as under root of 1 plus y dash square. So I hope this right hand side of this expression is also clear and left hand side is also clear, and here's the explanation for that, right? And I explained you earlier how when you bring dx here, it becomes the second derivative, because this itself is the change in the first derivative, this term minus this term, right? So now how to solve this differential equation? Okay, so this is a second order differential equation, and the good thing is that here we have d square y by dx square, and here we have dy by dx, but there is no y coming directly. So what I can do, I can write dy by dx as z. So if you write dy by dx as z, then this becomes first order differential equation, and then z represents what? Z now represents the slope of the catenary, right? Okay, and so this becomes, since y dash is z, so y double dash becomes z dash or dz by dx. So this equation simplifies to f into dz by dx is equal to rho g into under root of 1 plus z square. Okay, so now this is the first order differential equation. If I am able to integrate this properly, then I'll be able to get z, and once I get z, then I can write z as a function of x, then I can write z as dy by dx, and then in principle I can get y as a function of x. So I hope the roadmap is clear, and now I just need to do the maths properly. Okay, so before doing the maths of this, I'll provide some preliminaries, because this leads us to special categories of functions. Of course, there's one way of putting z equal to tan theta, and you can use the conventional method that you've learned in JEE. But I would like to take this opportunity to introduce you to the hyperbolic trigonometric functions. So on the next slide, I am going to tell you about the hyperbolic trigonometric functions and how they can be used for solving this type of integrals. Okay, so understanding hyperbolic functions. So we define hyperbolic sine. We can also call them as hyperbolic trigonometric functions. So hyperbolic sine is defined as e to the power x minus e to the power minus x divided by 2. This is called the sine hyperbolic of x. Okay, sometimes it's called shine x. Okay, that's what I read somewhere. So some people say shine x instead of sine hyperbolic x, you can call it shine x. So shine x is e to the power x minus e to the power minus x divided by 2, and its derivative is what? Its derivative is this function, right? E to the power x plus e to the power minus x divided by 2, and this function has a name of itself, and it's called cos of x, cos hyperbolic of x, or cos x. Okay, and we can easily see that derivative of sine hyperbolic is cos hyperbolic here, and derivative of cos hyperbolic is sine hyperbolic. So somewhat similar to normal trigonometry, except for some pluses and minuses are going here and there, right? But that's why it's called hyperbolic trigonometry. These functions have some behavior like trigonometric functional behavior. Okay, some similarity is there. Okay, now another identity that I'll be using for doing my problem is that cos square x minus sine square x is 1. That you can easily prove. You can just substitute these functions, and you can easily see that e to the power 2x things will vanish, and you'll just be left with a 1. So cos square x minus sine square x is 1. Okay, this I'm going to use later on. Okay, and now another result that I'll be using is that prove that integration from 0 to z 1 by root of 1 plus z square is sine inverse of z. So this I want to prove. This result is required for precisely solving that differential equation. You see, our differential equation is what? F dz by dx is equal to rho g under root of 1 plus z square. So if you bring 1 plus z square under root here, then the right side will be rho g upon f into dx. So precisely this is the equation that we want to solve, and that's what I am doing here, and I'll use this directly later on. Okay, So now for solving this, we put z is equal to e to the power x minus e to the power minus x divided by 2. That substitution I am using, okay, which is also sine hyperbolic of x. So see, that's how I had defined sine hyperbolic sine x. So I put z is equal to sine x or e to the power x minus e to the power minus x divided by 2. So then what is 1 plus z square? So 1 plus z square is what? You just square it and you add 1. It becomes nothing but cos square x. I could okay, I could also say that from here itself. See, 1 plus sine square x is cos square x. But just to do the maths and explain by expanding, so you get this, right? So 1 plus z square becomes cos square x, right? From here also you can see. And why this substitution is going to help us, because now it becomes cos square x and you take the under root, then it simply becomes cos x in the denominator. So there's cos x in the denominator, okay, dz. So dz becomes okay, so denominator becomes cos x. So what about dz? So if z is sine x, then dz by dx is cos x. So dz becomes simply cos x dx, right? So see the beauty. So this is also cos x and the numerator becomes cos x dx. So now cos x cancels. So this is what you get, cos x upon cos x dx. And what about the limits? So you are integrating from 0 to z. So if you put z is equal to sine of x, then x becomes sine inverse of z. So here the limits become, you have to put the limits for x. So here you put sine inverse of z, okay. And if you solve this, then integration of dx is dx, and you at 0 that value will be 0, and at sine inverse of z it will be sine inverse of z. That's it. So integration from 0 to z, 1 by root of 1 by plus z square is nothing but sine inverse of z. So this I am going to use later on in solving that differential equation, okay. So a little bit of hyperbolic trigonometry, some functions you should know for solving the catenary problem, and these functions might appear somewhere else also in physics. At places you might get trigonometric, hyperbolic trigonometry, okay. So this much is sufficient for now. I'll also state some more identities which you might like to explore on your own, and you might like to prove. So these are the so these are the various trigonometric identities. There are lot more identities, just some simpler ones I have put here. Out of this I'll be using two particular identities. This one I'm going to use. Cos of x minus y is cos x cos y minus sine x sine y. So this I'm going to use. And another one that I'm going to use is the double angle or half angle formula. So cos 2x is cos square x plus sine square x, okay. So these two things I'm going to use in my video also, but other identities I'm not going to use. If you want, out of your interest, you might like to prove them, okay. Now coming back to the differential equation, see, this was the differential equation. F dz by dx is equal to rho g under root of 1 plus z square. So I've just separated the variables and written this differential equation once again. So dz upon under root of 1 plus z square is rho g by f into integration of dx. And our catenary was going like this, and this is x equal to 0. Here the slope is 0. So z was y dash, right? That was supposed to be slope. So that's why at x equal to 0 the slope is 0. So that's what I put, 0 and 0. And at x equal to x, slope is z, okay. So just integrate this, and this is what you get. So sine inverse of z is rho g x by f, or we can say that if you okay, this is the identity that this is the definition of sine x, okay. So from this, if you rearrange this, you get z is equal to sine of rho g x by f, okay. So since we have done a definite integration after fixing the origin, so we do not need an arbitrary constant so far, except for another arbitrary constant, which is f. F of course is still an unknown, but we didn't get a plus c because we fixed the origin at x equal to 0, y equal to 0, which was the bottommost point of the catenary, and we already used the fact that the slope is 0 over there, okay. And now for simplicity of maths, because I do not want to carry this rho g by f everywhere, so I just put it as alpha. So then see, z is nothing but dy by dx. So instead of z I have put a dy by dx, and right hand side becomes then sine of alpha x, right? Now we need to integrate it once again to get the shape of the catenary, okay. So now from 0 to y, at x equal to 0, y is 0, because that's how the origin is defined, right? So here x is 0, y is 0, and at x equal to x, y is y, so 0 to x and 0 to y. So and sine of alpha x, you saw the integration, so this integration will be cos of alpha x divided by alpha, right? So that's what I've written. So this becomes cos of alpha x divided by alpha, and then you need to also put the limit. So remember that at x equal to 0, cos of alpha x is not 0. So if you put x equal to 0, this will be half, right? So that's why I'm getting a minus half over here. At x equal to x, this is cos of x, and at x equal to 0, this will be 1 by 2. E to the power 0 is 1, e to the power minus 0 is 1, and upon 2. So therefore I am getting a minus half. And this is our required equation, okay? And here if you see right now, alpha is still an unknown, which I need to estimate using the conditions of the problem, okay? But this is the general equation of the catenary. Alpha can vary situation to situation, okay? Now how can we estimate the alpha? That was our part B. So we can estimate alpha using the fact that, see, bottommost point, I mean this hanging point and this hanging point, the vertical separation is lambda, and let us say this coordinate is minus of x naught from origin to this wall. Left wall is, let's say left wall coordinate is minus x naught. Since this whole distance is d, so right wall coordinate is d minus x naught, okay? So I can say that value of y at d minus x naught minus value of y at minus x naught, this should be equal to lambda, right? I think I've messed it up a little bit, although final calculations I've done right, but let me try to correct it here. So it should have been y of d minus x naught, this should have been plus over here, and this should have been a minus over here, right? And accordingly, okay, so y was this, so alpha, if you take there, that will become lambda alpha, and there will be a minus sign then over here, and there will be a plus sign over here then, okay? So this is one condition, okay? And the other condition is that the length of the rope is L. So length of the rope can be written as what? So any small segment length is under root of dx square plus dy square, right? So you can take dx common, so it becomes dx into under root of 1 plus dy by dx square, right? So that is your dl, and you can find the length, and this is nothing but y dash. So length of the segment from minus x naught to, it should have been again d minus x naught, it should have been d minus x naught. So okay, so this should be equal to L, right? Okay, and okay, and y dash is nothing but sine of y dash is the sine of alpha x from equation 10. See, what is equation 10? This is the equation 10. So y dash will be what? So this will be cos alpha, derivative will be sine alpha, and there will be alpha multiplied because of the chain rule, okay? So and alpha cancels alpha, so this becomes sine of alpha x. So this is sine of alpha x and dx, and sine alpha x dx integration will be what? That will be cos alpha divided by alpha, okay? Okay, so using equation 14 in 13, so you put it over here, and this becomes then just a sec, so cos alpha x, if you put here, this becomes sine under root, so sine, yes, but there was supposed to be an integration also, so just a sec, so y dash is sine, sorry, y dash was sine of x, so under root of 1 plus y dash, this becomes cos, and once you integrate this, then it again gets into sine, so this is correct. So sine of again I messed up positive and negative signs here, so let me again correct. There should have been a minus sign over here, and there should have been a plus sign over here, because upper limit is d minus x naught, okay? I've somehow messed up this negative and positive signs in such a way that my final answer is correct, okay? So okay, okay, so this is the other condition. So let's just go with the flow and understand the principle. So maths I might have messed up here and there, okay? So this is one equation that we get by using the fact that the length of the curve is constant, right? So this is equation number 15, or you take alpha over there, then it becomes again there should be a minus over here and a plus over here. I hope I'm doing it right now, correct? So this is equation 16. Okay, now I need to eliminate x naught. So how do I do that? So see, there is an x naught in equation 16 and there is also an x naught in equation 12. Okay, equation 12 we got by subtracting this coordinate and this coordinate, so and equating it to lambda. So now what I can do is that, see, there is minus cos of alpha minus alpha x naught, and there is sine hyperbolic of there, where's the alpha? Again there should have been alpha also. I've done so many mistakes, but I hope you are still understanding the things. So there should be an alpha over here, there should be alpha over here, alpha over here, and alpha over here. Okay, and recall the identity that we have here. The identity is that this one, cos square x minus sine square of x is 1. So if I square this one, the equation number 12, see, equation 12 is here. So if I take the whole square of this, I am going to get cos square of alpha x naught, and here if I square this equation number 16, I'll get sine square of alpha x naught, and if you subtract the two, you will get 1, and there will also be two AB type of terms coming, but you see some simplification will happen. This square, when you subtract it from this squared, that again will give you 1, and if you simplify that, finally if you simplify that, what you get, and also you can use now for you will get sine and I mean two AB type of terms you will be getting, and if you use the simplification, that cos of u minus v is cos u cos v minus sine u sine v. If you do the whole maths, just substitute and do the whole maths, this is the final equation that you get, that cos alpha d minus 2 becomes alpha square into L square minus lambda square. And now you can also use the half angle formula to simplify it further, and this is the final result that you get. So that was my analysis of the catenary problem. I messed up in so many places, but I promise you the final result is correct. You can try doing the maths. It's not very difficult maths, you just have to pull it through meticulously. So that's my analysis, and I hope you liked the video. If you liked the video, please do give it a thumbs up, and please share this video as much as possible with your friends through WhatsApp groups, Telegram groups, Discord servers, or whatever media you use for networking with your fellow students. And most importantly, if you have not already subscribed to my channel, please do subscribe to my channel, because that's what keeps me motivated to post a new video every day. Thanks a lot for watching this video, and as always, God bless you all. Thank you.